So this is the next lecture on topology separation axioms. In previous videos we have seen definitions, examples, theorems about T0 space and T1 space. That means Kolmogorov space and Freche space. So today we will go ahead with T2 spaces. The most important among all the spaces are T2 spaces, also known as Hausdorff spaces. So these are T2 spaces, what we are going to learn about today. So first of all, definition. What the definition is? First I'll try to make you understand this definition through the diagram. So here is your X with a topology tau defined on it. So X tau is a topological space. When we were studying T0 space, the condition was if you take any two distinct points here, you will either get an open set containing X and not containing Y, or you will have an open set containing Y and not containing X. When we moved on to the T1 spaces, the condition changed, and the condition was for every two distinct points X and Y here, you should have an open set G containing X and not containing Y, and an open set H containing Y and not containing X. In T2 space, the condition is there the same, but an additional condition is there to define the T2 space. So what the additional condition is? So let X tau be a topological space, X tau is said to be a T2 space, also known as Hausdorff space, if for every two distinct points X and Y in the space X, this set X, we have open sets G and H such that X belongs to G, Y belongs to H, and G intersection H is phi. That means G and H are now disjoint sets. In T1 spaces, the condition was that if here is X, here is Y, you can have G like this, you can have H like this. So if this condition is satisfied, it will be T1, but it will not be T2, because here intersection of G and H is not phi. So if the space is to be T2 space, what additional condition is there? That your G and H should be disjoint, and this condition should be satisfied for every two distinct points X and Y, whatever the 2 points you are taking within the set X. You take a point X here, you take a point Y here, you must have an open set containing X and you must have an open set containing Y, and these two open sets must be disjoint. That is the additional condition here from T1 space. T1 space, you were not having this condition that the two sets G and H must be disjoint, but in the T2 spaces, this is the additional condition that two open sets G and H must exist such that X is in G, Y is in H. But the additional condition is that the intersection of G and H should be phi. That means G and H should be two disjoint sets. Now this is the definition. I think you must have understood what a T2 set, what a Hausdorff space is. Now we move on to the examples. So the very first example is discrete topological space. So discrete topological space, on a set X, whatever the set X may be, is a T2 space. Now we will show how. So let X be the set and tau be the topology. So I'll denote this tau by D as I'm talking about the discrete topology. So I'll denote the topology by D instead of tau. So now we will prove that this topological space is a T2 space, a Hausdorff space. How? Let X and Y be two distinct points of the set X. Now what I want two open sets G and H, G containing X, H containing Y, and G and H must also be disjoint. And in case of discrete space, it is very easy. Why? Because in discrete topological space, every subset of X is open. So why not to take the easiest one, the singleton set X and the singleton set Y. Take it as your G, take it as your H. Now your open set G contains X, your open set H contains Y, and their intersection is phi. Why? Because X and Y are distinct elements. X is here but is not here. Y is here but is not here. So intersection of these two sets is phi. So there exist two open sets, G and H, G containing X, Y containing H containing Y, and their intersection is phi. So this topological space, that means the discrete topological space, is a T2 space. What about indiscrete topological space? So if we talk about indiscrete topological space, let X be any set, and let us denote by I the indiscrete topology defined on X. What will happen? If you take any 2 points X and Y, distinct points from X, now what you want? You want two open sets, one containing X and not containing Y, other containing Y and not containing X, or you can say that their intersection is phi. In case of indiscrete topology, we know that there are only two open sets, namely phi and X. So here you are having only two sets. These should be your G and H. But the fact is, your G, if you are taking this set as G, your G is neither containing of these two elements, and H is containing both of these elements. So you are unable to find two open sets, G and H, G containing X, H containing Y, and their intersection is phi. Because here you are having only two open sets. There are no more open sets. So you are having no choice. The only choice is phi and X, and phi and X does not satisfy your required condition. So indiscrete topological space is not a T2 space, is not a Hausdorff space. Next is the example of topological space induced by a metric space. Topological space induced by a metric space. Now we will talk about this topological space. So let X be your set and tau be the topological space induced by the metric D defined on X. So now here is your X and here is your topology. This is X and tau. You take any 2 points X and Y, distinct points. So let X and Y be two distinct points from X. Since it is the topological space induced by the metric D, so we can talk of dxy. And in usual sense you can say dxy is the distance between the points x and y. This is your dxy. Now take your m as dxy by 3. That means I have trisected this distance. So this is here and here. This is your m, this is your m, this is your m. M plus m plus m, 3m. And your 3m is actually dxy, the distance between x and y. Now consider the open ball B centered at x end of radius m. Similarly, consider the open ball B centered at y of radius m. So what we are talking about? One open ball is here, another open ball is here. Name this open ball as G and name this open ball as H. We know very well that in a topological space induced by a metric space, every open ball is an open set. So G is an open set as well as H is an open set. So G and H are two open sets. From diagram, it is very much clear that your G contains X, your H contains Y, and their intersection is Y. So you can say there exist, you can say open sets, there exist open sets G, that means open ball centered at X of radius M, and open set H of with center at Y and radius M. So here you have two open sets G and H such that your G contains X, your H contains Y, and G intersection H is phi. That means G and H are disjoint sets, and that is the required condition for a topological space to be a T2 space. So this topological space induced by a metric space is now a T2 space, is a Hausdorff space. So it was another example, and now we will move on to another example, the third one. I'm talking about the third one because the second, that means the indiscrete topology, that was not a T2 space. So we have, till now we are having two examples. One is of discrete topological space, the other one is the topological space induced by the metric D. And now the third one. What about co-countable topological space defined on an uncountable set? Question mark. Will it be T2 or will it not be a T2 space? So let us check whether it will form a T2 space, Hausdorff space or not. So let X be a set which is uncountable set. So I have an uncountable set X, and tau is a topology that is co-countable topology defined on this set. That means this tau contains, which sets will be there in this topology tau? One of them will be phi definitely because it is a topology, so phi must be there. And then a subset of X such that a complement is countable. A complement is countable. Now we will show that this topological space X tau is not a T2 space. So how we will prove that? We will prove it by the method of contradiction. So first we will suppose that it is a T2 space, a Hausdorff space, and then we will arrive at some contradiction showing that this topological space, that means the co-countable topological space, is not a T2 space. So first I suppose that, suppose that X top is a T2 space. This I have supposed. That means if I take any 2 points, let X and Y be any 2 distinct points of X, then since we have assumed that this is a T2 space, there must exist open sets G and H such that your point X is in G, your point Y is in H, and your G intersection H is phi. Because you have assumed that this is a T2 space, these two sets must exist. Now, G is open set, H is open set, and the topology is co-countable. In co-countable topology, a set is open if its complement is countable. So G and H are open sets. So this means G complement and H complement are countable sets. Why? I repeat, because G is open, and in co-countable topological space, a set is open if and only if its complement is countable. Complement is countable. So G is open, so G complement is countable. H is open, so H complement is countable. Now come on to this condition that G intersection H is phi. Taking complement on both sides, G intersection H complement will be the whole space X, and here apply the De Morgan's law of set theory. So what you will get? You will get G complement union H complement is equal to X. Now what is G G complement? It is a countable set, and H complement is also a countable set. This is a countable set, this is a countable set, and we know that union of two countable sets is also a countable set. That means X is a countable set. So it means X is a countable set, and this is a contradiction. Why? Because X is given to be uncountable set. So that means we have arrived at a contradiction. And if we arrive at a contradiction, that means our supposition was wrong. And what we have supposed? We have supposed that the space X tau is a T2 space, which is not correct, as we have arrived at some contradiction. So this topological space is not a T2 space. So what we have proved, that co-countable topology on an uncountable set is not a T2 space, is not a Hausdorff space. So I am writing here, co-countable topological space defined on an uncountable space is not a correct space. So is not a T2 space. On the same lines, what we have just proved, on the same lines, we can prove that co-finite topological space defined on an infinite set is not a T2 space. On the same lines, what we will do, we will take 2 points X and Y from the infinite set, and then since we have assumed that the topological space is T2, we must have 2 open sets G and H such that X is in G and Y is in H, and G intersection H is phi. G intersection H is phi will give you G complement union H complement is X, and G H are open means G complement and H complement are finite. If G complement and H complement are finite, then their union G complement union H complement must also be a finite set. But G complement union H complement will be equal to X, which will imply X is a finite set, which will be again be a contradiction because X is given to be an infinite set. So that means cofinite topological space defined on an infinite set is not a T2 space. So this will be a theorem that can be proved on the same lines on the proof of the previous theorem. One thing is to be noted that if a space is T2, then it must also be T1 space, because there is an additional condition. There is only an additional condition. Similarly, if a space is T1, then it must be T0 on the same lines, because there is an additional condition. Here, what you are having, that either there will be an open set G containing X and not Y, or there will be an open set H containing Y and not containing X. And here you are having that both the open sets G and H must be there. If both are there, then at least one of them is already there. If there are two open sets G and H containing X and Y whose intersection is phi, then relieve the condition that G intersection H is phi. That means you are already having two open sets G and H, G containing X, not Y, and H containing Y, not X. So this condition directly implies this, and this condition directly implies this. So here I am going to stop this video. In the next video, we will prove some more theorems on Hausdorff space, maybe including Pratchett and Kolmogorov space, maybe not, but we'll do more and more theorems and more results on T2 spaces. Till then, thanks. Wait for the next video. Thank you.